Thank you all very much. I'm just going to start with a quick picture here because, it's always nice to see a full room. I was just noting that a talk last year was 6 people, and it was still excellent because there was a good bit of back and forth. So I'm here today to talk to you about monitoring Kafka. We had an excellent talk yesterday from Gwen Shapira and Xavier on monitoring. They covered several different areas. This talk is not going to start with what is Kafka. Thankfully, here at Kafka Summit, I can at least assume that everyone in the room has a basic understanding of what Kafka is, or you've gone to another talk that's gotten you that information. I'm also not going to be talking about an encyclopedic knowledge of monitoring or even monitoring Kafka. I'm not going to hit every metric that you should have. I'm going to hit some key metrics and some key information for how to do it and not make the same mistakes that I am currently making. I'm also not going to talk about automation. Automating responses to metrics and alerts is great. You should do it. I should do it more. These are all things that you can cover in a lot of operations talks. So why are we talking about monitoring at all? So, LinkedIn runs a pretty large Kafka installation, and monitoring is very front of mind for me right now. We're running into a number of issues. I recently wrote a post for a site, devops.com, on something called Code Yellow. Code Yellow is a process that LinkedIn uses to deal with applications or teams that are in crisis. Often it deals with communications problems in teams, tech debt that's built up in an application to a point where it's unsustainable, or in our case, explosive growth that we weren't expecting. As you can guess from me writing an article and being a Kafka SRE at LinkedIn, we are currently in a Code Yellow for Kafka and dealing with digging ourselves out of the hole we're in. Why are we there? So we started using Kafka, let's say 2010, before it was open sourced. In 2015, September, we announced 1 trillion messages a day. Yay! In 2017, last year at San Francisco, I noted that we had hit 2 trillion messages a day. Yay! The end of 2017, we hit 3 trillion messages a day. And then about 3 months later, just last month, we hit 5 trillion messages a day. So we added 2 trillion messages in 3 months. That hockey stick graph is my current sleepless nights. So that's why I'm here talking to you. That's the hole we're digging ourselves out of right now. So we're actually in the process of overhauling our monitoring, and we're following some of the things that I'm talking about in the talk today. So what is monitoring not? Why am I in this situation? We forgot that monitoring is not alerting. They are not the same thing. You should be collecting everything. Kafka has hundreds upon thousands of metrics, and we have per topic metrics and per partition metrics. You should collect these as much as possible. They're going to be useful for debugging problems. But you should be alerting on almost none of them. They will all add noise, they will all create problems, and you won't be able to figure out what half of them mean most of the time. So events are better than metrics, and thankfully we do have some events. It was great that Jay talked about that yesterday because events are just as important in monitoring, and well, we use Kafka for monitoring as well. Thankfully we don't monitor Kafka with Kafka anymore. That's a whole other talk that I've done. Tests are better than alerts. We've run into several situations. One that I was recently talking about with my manager was around file descriptors. Kafka had a leak in socket handling not too long back, and we ran into situations where we exhausted the number of file handles allocated to the application. So we added alerts for file handles to deal with this situation, and the code was fixed. And we still have the alert. And the alert has gone off in stupid situations where it really didn't matter. We hit the 60% threshold, and it wasn't important. What we didn't do, and what we need to do, is we need to move that back to a test. So instead of alerting on this, we need to test before we release the code that it does not excessively use file handles. And we need to do this with memory and CPU and everything else as well. The best thing that you can do is optimize your alerting for the amount of sleep that you would like to get. And I say this as someone who has a 12/7 rotation, and I hand off to Bangalore at 7 o'clock every night so I can always sleep at night. Yeah, they still wake me up. They still call me at 2 a.m. when there's a problem that they can't figure out, or when they have an alert that's going off that's unclear to them what it means. So what we need to get back to with monitoring is our service level objectives. And you've probably heard SLO or SLA before. An SLA is not an SLO. Most of us do not have SLAs to deal with when we're dealing with internal customers. What we have are SLOs. A service level agreement is exactly that. It's a contract. It's an SLO with teeth. It has a penalty associated with it. As a bank, you may have an SLA with your customers, especially your business customers, where if you don't fulfill the things that you've guaranteed to them, you're going to pay them some amount of money. I used to work at VeriSign, and running .com and .net, our SLA agreement with ICANN was $1 million a day if we did not make 5 nines of uptime. So that's, I mean, there's incredible drive there to take no risk at that point. So when we're talking about SLOs for Kafka, what are we usually talking about? Availability and latency are the 2 big ones. But really, they're any guarantee that you make to your customer. Anything that you tell your customer, this will always be true. And if it's not true, you can be assured that I'm working on it. For us, it's availability and it's latency. Speaking about availability, what do I hold myself to right now? 4 nines. 4 nines is pretty significant for a system like Kafka. I have referred to Kafka many times, even this week, as a developer proof of concept that we all run in production. It is amazing that it works at the scale that it does. So I promised you 3 metrics in the title of this talk, and I will give you 3 metrics. I will give you more. However, I did trick you. You're going to hear some things about these metrics that you may not have expected. So the 3 that I'm going to talk about are under-replicated partitions, request handlers, and request timing. So under-replicated partitions, of course, are partitions that are not fully replicated within a Kafka cluster. We have replication factor 2 or 3 or 4, and when you're down 1, you'll get an increase in this metric. The request handlers, and specifically the request handler pool idle ratio, is the metric that I'll be talking about next. This is really the overall utilization of the Apache Kafka broker. It's kind of like a CPU metric for Kafka. And the last one I'll be talking about is actually a set of metrics. It is the request timing metrics. Kafka provides a full set of 6 timing metrics for each request type, and they tell you how long requests are taking in each stage of processing, and they are very, very interesting to look at. So getting started with under-replicated partitions. These are very highly discussed. I actually devoted several pages in a book you may have seen to talking about this particular metric and how to decode it. It describes overall cluster health, and it exposes problems both on the consumer and the producer side, because replication by its very nature is consuming from the leader broker and producing to the follower broker. Now the produce process is a little bit different, but it shares some of the same features as regular producing, specifically writing to disk. So this is what a failed broker looks like when you're dealing with the under-replicated partitions metric. You have a high level of under-replicated partitions that is consistent for a period of time. Now, in this case, shortly after noon, this broker had a hardware failure and it went offline. And then it took us several hours before we were able to get that system rebooted and back online. And as soon as we did, it caught up. Everything was clean again. So this is great. Under-replicated partitions tells us about a failed broker. Under-replicated partitions also tells us about consumer-side issues. So in this case, we have one broker that has a variable level of under-replicated partitions. And it's the leader that reports under-replicated partitions for its followers. So in this case, it's kind of flopping around. This tells us that that broker is probably having a problem serving out those requests. So it's having a problem either reading the data out of memory, reading it out of disk, or serving it to the client, so it may be a network issue of some sort. I don't really know what's going on here. This is not nearly as clear as the failed broker is. And then we have this one. This is a fun graph. This is more of a producer side problem. This is where we have a number of brokers in the cluster that have a variable amount of under-replicated partitions. So we've got problems all over the place. This could be one broker that is failing to replicate from all of these different brokers properly. It could be multiple brokers that are having a problem. I can't really tell from the graph. Now, if I sort all the metrics underneath and see which ones are 0, I may see that there's one that is 0 all the time, and that's going to be my problem broker. Or I can use the CLI tools to enumerate all of the under-replicated partitions and see if there's a common thread. But when we're talking about the under-replicated partitions metric, the most important thing that it is to you is completely overrated. It doesn't map to your SLOs at all. It doesn't give you a clear signal. it's often not actionable. You look at it and you have no idea what you're supposed to be doing. You have to do more digging to find out whether or not it's actually an issue. And when I say it doesn't map to your SLO, for the most part, your customers do not care if you're not replicating the data within the Kafka cluster. They can still produce it, they can still consume it. And if their availability is fine and their latency is fine, they really don't care what's going on here. So this is one of these metrics that you should collect, but not necessarily alert on, because you're not going to know what to do all the time, and half the time you're going to leave it sitting there for hours and hours and hours until some other situation resolves itself. I have clearer metrics for a system being down than this one. So this is the theme you're going to see, what works and what doesn't through the rest of this talk. So moving on to thread pools. Kafka has specialized thread pools for all types of things, just like any modern application that's doing request processing. We have thread pools for log compaction. We have thread pools for log segment recovery, which, if you didn't know, are also used at broker startup and broker shutdown. So those recovery thread pools, not just for unclean startup. We have network handler pools. We have request handler pools, and I'm sure we have a couple other pools that I've forgotten about because they're in the back-end processing and we don't see them that much. Now, network and request handler pools, those are the ones that are most important to your clients. The network handler pools, not so much. All those threads do is handle the connection itself, read the bytes off the wire, and write the bytes back to the wire. They actually don't do very much work at all, and you don't need a lot of them, because the network handlers hand off everything to the request handlers. The request handlers are where all the work is done. These are the threads that decode and validate the protocol. They perform the actual task, whether that's consume, produce, offset requests, metadata requests, whatever it is. They do all of that work. They wait for answers from the other brokers when there needs to be coordination with the rest of the cluster. And then they assemble the response to send back to the client. At that point, they hand it back off to the network thread, and you go back to the client, and everything's happy. So your request handlers are quite busy. They do provide a good look into what the cluster is doing overall, what its utilization is. Just like a CPU load metric, it's going to give you information about how utilized Kafka is. So there are three major things that we look at when there's a problem with the request handlers. Now, this is a metric that is between 0 and 1. 1 is 100% idle. So 1 is great. 1 means you're not busy at all. 0 is bad. 0 is you're completely saturated. So we have CPU time problems, timeouts, and deadlocks. CPU, anything that causes Kafka to expend CPU cycles is going to result in this metric going down. This includes problems related to failing disks, because you'll see increased I/O weight, so the request handlers will spend longer accessing the disks. And it also, especially now with the prevalence of SSL, and if you have compression going on, you're going to use up a lot of CPU there. Timeouts and deadlocks, these are a little trickier to deal with. So this is what a timeout or a deadlock looks like in your Kafka clusters when on the request handler idle ratio. You can see it very quickly drops down to 0 availability. And we're hitting this on multiple brokers. Now, this particular case is a deadlock. There is a deadlock in some of the shutdown code. Thankfully, you don't have to worry about it, because it's deadlock in the shutdown code related to the authorizer module that LinkedIn wrote to integrate with our authorization system in-house. So there was a bad interaction there that's causing it to shut down. This bounce was actually just from yesterday when we were fixing the problem. Timeouts and deadlocks, though, look exactly the same. Timeouts typically come in when you have controller requests that are failing to be processed in time. What happens is the controller sends a request to the broker, and this happens most often at broker startup. The controller sends this giant leader in ISR request to the broker and tells it, here's all the partitions you should know about. Start up all your replica fetchers. And the request handler starts churning through that. And let's say you have a controller request timeout of 1 minute. And that processing takes 10 minutes. After a minute, the controller says, well, he didn't answer. Let me send the request again. And it ties up a second request thread. And a minute later, it said, well, he didn't answer. Let me send it again. It ties up another request thread. And all of a sudden, you have that. Your saturation on the broker goes to 0. You have no threads left. Everything is processing the controller request until one of them finally finishes and the broker can answer quickly saying, okay, they're already done. Don't send me any more requests. Really, I need to talk to my customers now. You're going to hit timeouts much more often than you hit deadlocks, thankfully. Deadlocks are code bugs. They're pretty rare. These are the types of situations that a lot of people in this room, myself included, are not going to be able to debug on their own. It's going to require someone with knowledge of the Kafka code to really dig in and see what's going on. Now hold on a sec, you say. Todd, brokers don't do compression anymore. You said that compression was a CPU problem, but with message format 1, we stopped doing that. We have relative offsets, and the produce requests don't have to be recompressed by the broker. Yeah, brokers shouldn't do compression, but they do. Ask me how I know. There are 2 situations that you're going to run into where the brokers are going to have to recompress messages. Up conversion of the messages and down conversion of the messages. Now, up conversion is one that we did not run into recently, but we have run into in the past. You have the Kafka cluster running a new version of the broker, and the message format, you've bumped up to the new version. But your clients are all still sending the old message format, which means that when that produce request comes into Kafka, it has to decompress the messages and validate them, and it always does that. It always calculates the CRCs. Then it has to reassign the offsets, write it to the new message format in memory, recompress it, and write it to disk. This is really bad. Down conversion is the other side of this, and this is the one that I saw a couple weeks ago. I was wondering why, on a relatively lightly loaded broker, we were running with about 20% idle ratio on the request handler pool. I used a profiling tool to generate a flame graph and saw that we were taking 80% of our CPU time in deflate, which, as you may know, is gzip compression. Turns out what we had done is we had rolled out a new version to the Kafka brokers. We hadn't bumped up the message format. We were keeping the message format at message format 1 because we know we have lots of old clients. So that was the right thing for us to do. Except we rolled out a producer client to do SSL that had the new message format. And all of those producers were sending with the new message format because the Kafka brokers would accept it. So what was happening was Kafka was expanding all of those messages saying, oh wait, I want to write this to the disk with message format 1. I have to rewrite all of these requests, recompress them, and write them down. We actually added some internal code to lock the API version so that the producers could not do this anymore and would be forced down to the old version. That's still internal. There are discussions about whether or not that's going to be upstream. There's also a KIP, I believe, that's under discussion with an alternate solution to this problem. But both of these situations you're going to see when you run into upgrades that are going on. And especially with a large environment like ours, it's impossible for me to get all of the clients to upgrade in lockstep. So these are actually pretty big problems, and you got to keep an eye out for them, even though we're not supposed to be doing this in Kafka anymore. So moving on from the request handlers to what they're actually doing, we'll talk about the request timing now. So I mentioned that there were 6 metrics for request timing that are provided, and these are provided for every request. Most of them are completely uninteresting to you. You probably don't really care about the request timing around stop replica requests. But consume and produce and offset fetches are probably very important to you, and especially if you have SLOs for latency. These are some of the metrics that you're going to want to look at because they do map directly to your SLOs for latency. So we have total time, which is how long the request handling takes from end to end. There's request queue time, which is how long that request spends waiting to be processed by the request handler, how long it takes before a request handler can pick it up. The local time is the work that is done local to the broker that the request is being processed on. So in the case of produce, this is the leader writing the request to disk. Then you have remote time. This is the amount of time that you spend waiting for other brokers to do something for that broker that's processing the request. With produce, if you have acknowledgement set to anything above 1 or -1, since -1 is technically not above 1, you're going to be waiting for other brokers to send acknowledgements back. This will be factored into the remote time for the requests. Then you have the response queue time, which is the amount of time after the request handler finishes that it waits to put the response back onto a network thread to send it back. And then there's the response send time, which is the amount of time to send to the client, but it's not really, because all it is the amount of time to get the request into the TCP buffers locally to send it back out. So it doesn't count all the network time that you're going to see. If you have a very long, high latency connection, like say from here to Singapore, you're going to see high latency, but it won't be reflected in the response send time as well as exactly as you would like it to be. So these metrics are great, but are they really usable to us? Let's look at a couple graphs here. This is the produced total time on a broker that is perfectly healthy. This broker's performing great. The scale may not be too visible here, but this is in milliseconds. The graph on the right is the average time. It's the 50th percentile time. For all of these metrics, we have 50th percentile, 75th percentile, 99th percentile, and 99.9th percentile. You also have an average and a max, which are the life of the process, so they're not quite as useful as we'd like them to be. And there's a rate metric as well. So in this case, the 50th percentile is from 0 to basically 8.5 milliseconds. Great. The scale on that other graph, which is the 99.9th percentile, is actually 0 to 9,000, so 9 seconds. So we can see we're off by several orders of magnitude here between our 50th and the 999th percentile. Why is this? This is the total time processing. Well, produce requests are not all equal. You have some produce requests that are really small batches. You've only got a few messages. You've got other produce requests, say from a mirror maker that's handling thousands of topics, that are really big. They have lots of partitions. They have lots of messages per batch. They take longer to process. So your total times aren't going to match up. You're going to have to be careful about what you're picking to alert on in this case. Now, when I say alert, also be careful about what you promise your customers. Because if you promise them that, oh, I'm going to process every request in 20 milliseconds, no problem, that's great. That only works for half of your requests. You still have to worry about these customers over here. So you need to decide where your breakdown is in that SLO for latency. Okay, fine. We won't use total time. Let's use local time. I mean, local time should be easy to use, shouldn't it? Well, once again, this metric on this side is actually from 0 to 1 millisecond. We can see that only one broker is actually bouncing back and forth here because the rest are they're all too short. It's way too quick. The other side, again, we're going from 0 to 2.6, 2.7 thousand there. What's the discrepancy? Again, it's the size of the requests. These requests are really tiny. They take a very short amount of time to write to disk. These requests are much larger. They take forever to write to disk. So again, we have to be careful about what we're defining as our SLOs. Fine. We'll use remote time. Remote time's got to be equal, right? 0 to 2, 0 to 4, essentially. 4,000, that is. Why? These requests have AX1. Those requests have AX all. So those requests are waiting for other brokers to answer, whereas most of our requests don't wait for any broker to answer. They're just waiting for the leader to answer. So these metrics are good, but you do have to be somewhat discretionary about how you use them. So it's great. I've got what? It's been 20 minutes, about 15, about 20 minutes or so. So I'm fine. I'm done. I gave you your 3 metrics. I'm going to sit here and stare at my phone. Okay. So what's missing? What didn't I cover? I only gave you one set of metric that was actually potentially useful, and I told you that it was really difficult to work with. The fact of the matter is that Kafka provides an excellent set of metrics for debugging. It does not provide an excellent set of metrics for actually monitoring your cluster. There's a very good reason for this. Jay, Neha, and June are developers. And when Kafka was written in 2010 and open sourced in 2011, it was written and run initially by developers. And that's great. The system is fantastic. I mean, the size of these conferences is a testament to how many people are using it and how well it works for all of us. But I didn't start at LinkedIn until the end of 2013. And even at that point, there was one ops guy. There was one SRE responsible for Kafka at LinkedIn. And at that time, LinkedIn was really the only large user of Kafka. Netflix and Uber and the rest were up and coming, but we were still the ones driving all the development. We were driving all the testing and anything around operability. So operability has been a latecomer in Kafka. We're definitely starting to build it a lot more now. We've identified a lot of cases where there are problems. But metrics, we've still got thousands and thousands of metrics that are absolutely useless to us as ops people. And the developers are still turning around and saying, no, you need to collect all of those. Because if there's ever a problem, I have to look at those to figure out what's going on. And no, wait, I can't possibly log less than a gigabyte of logs an hour. I know you can't read them at all, but they're really important where there's a problem. And yes, I need that 10 megabyte log line that describes every single replica in the cluster on every single broker. Because how else am I supposed to know whether or not Kafka did the right thing? So where does this leave us as operations? It leaves us with developing external measures for Kafka. And we've done a few of these. Some of them are quite important. The first one is when it comes to availability monitoring. Now, this is really one of the most important parts of your SLOs, is whether or not the system is up and available to serve requests. Even if latency is an SLO, your customers probably care about whether the request goes out at all, a lot more than whether or not they care if it takes a second or 100 milliseconds. They can probably deal with latency a little better than they can deal with down and not working. This has to be measured externally. You cannot measure availability of a system from within the system. So the Kafka broker can tell you that everything's up and running and everything's perfectly fine, and you can even see requests coming through and it looks great. But if your clients have a network partition, you're not going to see it. If the requests are all being rejected with an error code that the broker thinks is absolutely fine, but the client is not happy about, there's going to be a problem. If your authorizer falls over, then you're not going to see that from the Kafka broker because the Kafka broker doesn't know that it's sending back a bad authorization error for every single request. So this is your client-focused monitoring. The last line there, and don't worry, all these slides get posted afterwards. They will be available to everyone. They'll be on my SlideShare. I'll tweet them out. They're going to be on the Kafka Summit site. You don't have to note down everything that I put up here. Kafka Monitor is a tool that we developed and we use internally to monitor all of our clusters. And what it does is it operates as a producer and a consumer. It produces messages to the Kafka cluster, and it actually assures that its topics have a partition on every single broker. So it's always looking at the balance of the cluster and rebalancing its own topics. And it produces messages, and the messages have some amount of information so that timing can be determined, because it then consumes the messages back out, assures that it got every single message, and it gives you metrics around the availability and the latency of those requests. So this is great, because this actually is a better latency measure than any of Kafka's internal numbers. Because once again, Kafka's internal request timings only tell me how long Kafka took to process the request. It doesn't tell me anything about the network. And as much as I would like to not be responsible for what the network guys do in my environment, my clients still see it as a Kafka problem at the end of the day. So I have to be conscious of that. Okay, one thing I did not talk at all about is operating system and hardware metrics. So let me ask you a question. Your Kafka cluster is running at 95% CPU across the board. Your availability is good. Your latency is good. What do? Anyone know what your response to that is? I'll tell you. It's to go get a coffee. Because there's no problem. What's causing 95% CPU? Is it Kafka? Is it a monitoring application? Is it CF Engine? Is it Puppet? You have no idea from looking at a CPU metric. CPU metrics are probably one of the most useless metrics that everyone monitors on their system. We monitored CPU load for a while and alerted off of it. And then I shut it off a week later because I couldn't deal with it anymore. And somebody just tried to turn it on while I was on vacation 2 weeks ago. And I came back from vacation and I grabbed my manager in a text message. And I'm like, Clark, what are you doing? Why are we turning on CPU? It's like, well, the development manager wanted to do this. I can't remember exactly why. I'm like, this is a bad idea. He's like, I'm going to put you in charge of responding to that. Thanks. So we don't know what it means. We don't know what's causing it. Memory's the same way. Have you guys ever seen a heap usage graph for an application that is properly tuned with a good heap usage size? It does this all the time. I can't get a signal out of that. So I don't want to alert on anything unless it has a 100% clear signal to me and 100% clear response. I have to know what it means and what to do all the time. A system being down is a clear signal and a clear response. If there is a Kafka broker down, I have metrics that tell me that with 100% certainty. I also know that I have two responses to that. I need to get that hardware back up, or I need to take it out of rotation in the cluster and move all the partitions off of it. So there is a clear thing for me to do. So I can monitor that. I can alert on that in addition to my SLO metrics. Anything else, I really shouldn't be bothering with. File handles, CPU, memory. If the system's up and running, I don't really care. If you have something that you know is going to be a problem eventually as it trends up, make it a warning. Don't make it wake you up at night. Because if you can go from the night until the morning after it crosses that threshold, don't stress over it. Just deal with it later. Get a coffee. So disk, when you're talking about operating system and hardware metrics, there are some interesting things here because we do need to monitor capacity of our system. And we need to plan for the eventual upgrade of our system as we need to add more disk or add more capacity. But these are things that you need to plan in advance. These are multi-factor, this is multi-factor monitoring. There are multiple things that you need to be conscious of when you're talking about the capacity of Kafka. Don't ever alert on this. There's a really good reason why you should never alert on this. You are not magicians. You cannot pull a server out of a hat and deploy it into a rack. That stuff has to be ordered weeks or months in advance. My lead time for hardware at one point was 6 months to get Kafka brokers just because of some supply chain issues. So I had to plan that far in advance for capacity. So that means that I have to look at these capacity metrics. These are the ones that I'm most interested in. Request handler idle ratio. I know I told you it was kind of useless. It's not here. I want to know the overall utilization of the system when I'm talking about capacity. Disk utilization, that's really important. I mean, as the disk, I have more data every day. The graph at the start of this was a testament to that. Partition count, this is one that we often don't think about. We have found, we do try to keep our brokers to about 10,000 partitions or fewer per broker. This is just the size of our hardware and the limitations that we found. But the Kafka cluster, as a cluster, the inter-cluster operations are very much driven by partition count. The higher the partition count, the larger your controller requests are, the longer they take to process. The more you run into that situation with timeouts in the request handler pools that then cause you sleepless nights. Network utilization is the last one. I've got 10 gig interfaces right now, so I don't really care about this as much. I can't push enough data through a single Kafka broker to saturate that at any point, but we'll get back there again. I mean, we'll get better CPUs. As Michael was noting in the previous talk, we get better hardware all the time and it gives us performance boosts. So eventually network will probably become my bottleneck again. Right now it's not. Right now my bottleneck is, I'm going to say partition count is actually my bottleneck right now. It's probably pretty tight between that and disk I/O. But doing this in advance is the key. You have to be looking at this months in advance. These metrics are things that you want to trend out and you want to look at them. Maybe you look at them quarterly, maybe you look at them weekly. What you don't do is look at them at 2 a.m. in the morning when you're running out of capacity because you have nothing you can do about it. And if you do happen to have servers sitting around at 2 a.m. in the morning that you can deploy onto, why didn't you do that at 2 p.m. the previous day? This is not tricky. These are the things that we have to know. So I mean, I may have 100 servers sitting around right now, but they're going to be deployed in the next week so that I actually don't ever want to go over 50% capacity on any broker. The reason for that is because if another broker in the cluster fails, I have the potential to double the load on any given broker, even in a perfectly balanced cluster, because it'll take over leadership for all the partitions it's a follower on. Now, if your replication factor is not 2, that math changes, but the same rules apply. So now I'm actually going to wrap up and move on to take some questions, and thankfully we'll have a good bit of time for that, I think. 5 minutes. Okay, a little less time than I planned on. So if you remember nothing else from today, define your service level objectives. These are going to be the important things that you need to monitor on. So monitor those service level objectives. And by monitor, I mean alert on those service level objectives because you need to know when you cross them. Metrics that cover lots of problems are noisy. Avoid them. Avoid crisp signal. Keep crisp signals wherever you can in your metrics. And buy my book. So, with that, these are some links. Again, they'll be available afterwards. Kafka Monitor, Burrow, of course, which we use for monitoring consumers. Cruise control. Our Apple friends noted that rebalancing is a problem. We use cruise control for that. And then some other tools we've developed. So thank you all very much. I appreciate it.
Raise your hand if you want to ask a question, and I'll hand you a microphone.
So you talked about planning in advance in terms of capacity, but in the first slide of your presentation, you showed in 3 months you went from 2 to 5 trillion messages. So how do you? That just scared me.
So I did also note at the time that this is a current problem that we're working back from. In that case, we do have capacity planning in place. We do review these metrics in advance, and I actually have to project out capacity for an entire year. And this year I had to project it out for a year and a half because LinkedIn's financial year is different than what Microsoft's financial year is. In this case, we actually hit a number of situations that we couldn't anticipate. We had a couple applications that ramped up external traffic and had to rebootstrap as a result, and resulted in a lot of extra data being produced. We had a number of initiatives that we're working on with Microsoft that we just could not project what the load would look like accurately. And then we had organic growth as well. In addition, we have GDPR coming in, and our focus over the last 8 months or so has been highly focused on GDPR, and we've ignored some of the signals that we should have been paying attention to. So, as I did note, we are trying to catch up on this now and make things better and putting these processes in place so we don't. Part of the code yellow is making sure that you never get to this state again, and that you put the processes in place so that that problem doesn't repeat.
I have 2 questions. The first one is, you said you had a SLO of 4.9. Is that for all your use cases, or do you have like flexible SLOs depending on things? Yeah, that's
let me hit that. Otherwise, I'll forget that before we. Yeah. So 4.9 is across the board. We hold that for all of our clusters. It's individually measured for each cluster. So we roll it up as all of production. Here's the number, but we actually look at it on a per cluster basis. That level of availability is sufficient for all of our use cases. We don't have any clusters that we hold to a lower availability. In our environment, we actually treat our staging environment at LinkedIn as production for Kafka, because all of the developers rely on us being up so that they can do their work.
Okay, and the second question, it seems like you've done a lot of work recently on getting the right signals out, etc. I was wondering if you maybe applied one of the methodologies that is being talked about recently, like Brendan Gregg has used, there's RED, there's one in the Google SRE book that I don't remember the acronym. I was just wondering like how you went about to do it.
Yeah, so for us, it's we're really doing this ad hoc internally. So we're looking at what works and what doesn't. We've got enough experience on it that we've got a pretty good idea of what's causing noise and what's not, and collecting that information. Now, speaking about Netflix's system, I did have some folks come to me recently after seeing SRECon talks in the US, wanting to implement some of the things that Netflix does around tracking failures within the entire system. And it's really some excellent ideas, and we're going to be looking at that shortly. But that's more focused on monitoring everyone else and not specifically Kafka. Unfortunately, when you're dealing with data infrastructure systems like Kafka, especially in an environment like LinkedIn or Google or Netflix, most of the tooling is designed for front-end applications. It's not designed to work with our stuff. So we kind of have to do our own thing most of the time.
What drives your decision to add new nodes to an existing cluster or spin up a new cluster?
So spinning up new clusters is generally driven by use case at this point. We have several people who Okay, so I have one customer who just came to me recently and said, so we've got this new project we're working on for messaging, and we want to have one topic per member ID. And I said, whoa, 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 hold on a sec. We're over 500 million members, and you want to cluster with a topic per member? No, let's talk about this and figure out what's going on. But they're going to end up with a dedicated cluster to do the things they want to do. We just need to figure out the right architecture. We also have some other dedicated clusters for data replication for databases. Right now, we're looking at what point do we need to federate Kafka clusters. So I have clusters that are approaching 150 brokers per cluster. And these are pretty large brokers. Netflix has done the same thing, but they had much smaller brokers when they hit these kind of numbers. So we're looking right now, what's the point at which we have to split a cluster in two, and what's the mechanic? How are we going to do that? How are we going to handle it in the client? We haven't hit that point yet. So right now, expanding clusters is what we do, and it's driven by those metrics that I talked about, mostly disk, request handler pool, and partition count, and getting them down into the right ranges.
Anyone else? All right, give it a,
One more. You know, and I'll be around for a little bit afterwards as well to answer any questions.
I think you got tantalizingly close to telling us which of the request timing metrics you would actually use and what sort of thresholds you would set. So I'm wondering if you're willing to give away anything that LinkedIn actually does alert on what those thresholds are.
I actually gave you the answer at the end. We wouldn't use any of them.
Okay.
None of them actually provide the measure that we would give to a customer of latency. So we're going to use the metrics out of Kafka Monitor for latency of requests to alert on, because that gives us the client view of the cluster, and that's really what I need to know. I don't need to know how long Kafka took processing the request, because processing the request may take 20 milliseconds, but adding on the network transport time may increase that past the SLO we provide them. So I always want to see what the client view is. Those request timing metrics are going to be useful to me in debugging a problem that Kafka Monitor tells me about.
Quick, small follow-up. Mm-hmm. Does Kafka Monitor send different message sizes or uniform?
I believe it sends a uniform message size. However, different message sizes would actually be an excellent improvement to that. So I'm going to go back and talk to my engineers internally, specifically Dong Lin, who open sourced that, and see what we can do.
Basically, the same question, more or less. If you define your SLO on the Kafka Monitor metrics, don't you have still the problem with the graphs you showed us earlier, that you have some producers who are producing like very large messages, or have just a completely different pattern of using your system than your monitoring tool does?
So it is very true. There is a different pattern there. In addition, synthetic monitoring like that does not tell me that a given topic is available. So it would be very easy for the Kafka Monitor topic to be up and running just fine. Meanwhile, the page view event topic is completely unavailable. So there are certain gaps there. Unfortunately, with the data infrastructure we have, we're not oriented at being able to inject synthetic traffic into random topics to be able to monitor that way. This is somewhere I'd like to get to. You do have to be careful with how much data you generate at that point. But I can provide my customers with an SLO defined off the Kafka Monitor metrics. So I can say that at a certain message size, the latency will be no more than X. And if their messages are, now I know that most of my messages that I have to deal with are maybe around 2K in size. So that's something reasonable. I can hit that point and give a guidance to our customers that is applicable for most of them. I can also monitor the dedicated clusters for different use cases with a different level. So in that case, I can go to our Espresso team, which is one of our databases, and say, okay, for your cluster, the latency will be this. They have different requirements around acknowledgements as well, so they have different concerns in place. It's really a matter of, at that point, it's fine-tuning the individual clusters for the client and trying to provide average guidance for everyone else.
Maybe just one note on that. The way we did it, we have a special flag on every message that is basically ignore.
Yeah.
And we can basically send to any topic.
Yep, and that's exactly what the approach we would take. The problem really just comes in is that we have thousands upon thousands of active schemas, and it's very difficult to engage with all the clients and get that changed across the board. Right now, as I've said, the last 6 to 8 months or so, we've been completely focused on upgrades that are necessary for GDPR, getting everyone to SSL, getting everyone to authorization. That took several across-the-board initiatives within LinkedIn to get everyone on board. Those are very painful for everyone, and we try to minimize them as much as possible.
Well, thank you, Todd. Let's give it up for Todd. Thank you for staying till the very end.
Thank you very much.
Don't forget to fill out your survey.